Our next speaker is Martin Bojowald. He'll be talking about the canonical description of quantum dynamics.
Thank you, and thanks to the organizers for giving me this opportunity here to speak. And it's already been very interesting. My background is more general relativity, quantum gravity, quantum cosmology. But we've been working on some methods initially for these areas, which turn out to be more general. And we also later noticed there are some precursors. So just as a brief introduction, so the main topic of this workshop, Koopman wave function, in very brief terms, makes classical mechanics look quantum. And there's a whole set of different approaches called effective theories that make quantum mechanics look classical. What I'm going to describe here is more in the second context. So it's based on, or at least initially started with this idea of developing methods for effective theories. But it works by deriving a geometrical picture of quantum dynamics from a certain parameterization of states that can also be used in comparisons between classical and quantum dynamics, or maybe coupling them at some point. So we started in 2006, and again, I'll later note some of the precursors that we found more recently. So just as a very simple example, how the parameterization of state works, we have, of course, well-known uncertainty relations. And there's a parameter on the right-hand side, this u, which in quantum mechanics has a specific value, h bar squared over 4. But it may be smaller or maybe even larger in other descriptions. And one example from this paper by some of our organizers is related to the fact that the density in these cases is not always positive in the Koopman case. And and so we would have, because uncertainty relations are fundamentally derived from positivity conditions on states, this u parameter could be smaller for Koopman wave function. So if we have dynamical aspects that directly relate to u, it will be easy to distinguish between different versions. Now, the starting point of this effective description that I'll use here is, it's probably very old, almost as old as Ehrenfest's theorem. So it starts with quantum mechanics. It is just quantum mechanics, really, just formulated differently, using expectation value equations. And so the usual commutator relationship with the Hamiltonian can be written in a classical type form, classical Hamiltonian dynamics, even though it's still full quantum. So we define the effective Hamiltonian as the expectation value of the Hamiltonian operator in any state. So that means we derive a function on state space. Rho might be pure or mixed at this point. The next step is also a definition. We define a Poisson bracket based on the commutator. So that means it's automatically anisymmetric and basically Jacobi identity. And then for products of expectation values, we just use the Leibniz rule to extend this to a full bracket on function space on state space. So that's not a hybrid bracket here, even though it looks classical on the left, quantum on the right. It's fully quantum. It's just a Poisson description of the commutator. And then with these two definitions, the quantum equation at the top is really just a set of coupled Hamilton's equations with the effective Hamiltonian on state space and the quantum Poisson bracket. Now, in general, that's very difficult as a set of equations to solve, because if we start with one operator and its expectation value usually couples to infinitely many other expectation values of independent operators. So to make this tractable, we need truncations. In simple cases, it might truncate automatically. In interesting cases, we have to do this by hand or by approximation. And a large class of examples is a semiclassical approximation. So we start with a basic set of operators like position and momentum, Q and P, and then consider only polynomials up to a certain order. So that gives us a finite set and usually requires truncations for general dynamics. Now, instead of just using polynomials, it's more convenient to use moments. So still the basic expectation values, which I'll just call Q and P without hats here. And then central moments in completely symmetric ordering is really derived from these polynomials, but it's a more convenient parameterization in most cases. So this would be a very general semiclassical approximation with a specific order that can be changed to improve it. Now, very simple example, the free particle. So in this case, it's a quadratic Hamiltonian, and so we don't really need a truncation. But it tells us something about the meaning of the moments. And this will lead us to the parameterization idea that I mentioned on the first slide. So if we apply the procedure, the effective Hamiltonian of the free particle is basically just the expectation value of p squared, which is the expectation value of p squared, standard kinetic term, plus a fluctuation term. So in this general moment notation, just the parentheses are a little bit displaced compared with the standard notation for delta p. But it's the same thing at second order. Now, the main question is, if we try to use this as an effective classical type description, is this delta p squared term another kinetic energy, or is there some potential contribution in it? So that's important for interpretations. And to check this, we can use these newly defined Poisson brackets on one of the previous slides. Because if it's kinetic, then delta p squared should really be just a momentum or square of a momentum. But if we work out these Poisson brackets for second order moments, there are two of them here. So there are 3 second order moments. 2 of the brackets include delta p. None of them has a constant on the right. So it's not obvious whether delta p is really a valid momentum in canonical terms. So at this point, the effective Hamiltonian is not that useful because we don't know whether there's just kinetic or also potential energy. Mathematically, there's a way to approach this question called the Casimir-Darboux theorem. It tells us that every Poisson manifold, so anything that has a Poisson bracket on it, can be formulated in terms of local coordinates, positions, momenta, and then possibly what's called Casimir functions or conserved quantities that have vanishing Poisson brackets with anything else. And so in particular, in an odd dimensional case, as in for second order moments, we need at least one of the C functions because Q's and P's always come in pairs and would give us an even dimension. So Q's and P's would then have canonical Poisson brackets, canonical deltas, and as I mentioned, C's Poisson commute with everything else. Now, we'll have to find these this version for the brackets here for second order. So brackets are copied here, and the Casimir-Darboux version has been known for some time. It's pretty simple. So one of the variables is really just the position fluctuation. The momentum is defined through the covariance Q and P. And then the momentum fluctuation or variance has 2 terms, the momentum squared of this S variable, and then a C here, so a single Casimir variable divided by S squared. And if we compute this product, delta Q squared, delta P squared minus delta Q P squared, that just happens to be equal to C. So C is bounded from below by this h bar squared over 4 in quantum mechanics, or as I mentioned in other approaches, might be smaller than that. So without this Casimir-Darboux connection, these variables have been found and used previously several times independently. First time was in the context of quantum field theory, 1979. And other examples are from quantum chaos, quantum chemistry, and more recently, quantum cosmology. Now we can apply this to the free particle. So because we now know that delta p squared has 2 contributions, we know there is a contribution to the potential. It's not just kinetic energy in the effective Hamiltonian. And this potential is just like a centrifugal term corresponding to the new kinetic energy. So we can remove the potential by transforming to an auxiliary plane instead of a single S, we have two variables x and y, some spurious angle phi here. And in terms of x and y, we'll just have really just kinetic energy, but we need this additional dimension for this potential-free description. And so here we can see how this geometry works. We have a completely geometrical solution of this quantum problem. So there's no potential in this xy plane, so just a straight line. But the angular momentum in this plane is given by this c parameter, which is bounded from below through the uncertainty relation. So the angular momentum cannot be zero, which means there has to be a certain impact parameter of the straight line with respect to the origin, given by angular momentum over momentum. The distance traveled, the momentum is constant here because there's no potential in the xy plane, so distance traveled is pt over m. And then s is just the radial distance. So if we just use the Pythagorean theorem here, we get the standard solution for s, which is our position fluctuation, and it's of the correct form, even for quantum mechanics. So that's an example of how this geometrical description works. And for someone who comes from relativity, it's usually a more intuitive interpretation. And then also we can compare different versions. So if we have a different lower bound for c, as in the Koopman case, then we would have a larger class of allowed solutions. Now, of course, the free particle is almost trivial. So the general description would be more like this here. So we have a generic Hamiltonian depending on Q and P, and then a formal Taylor expansion around the expectation values of Q and P gives us the effective Hamiltonian. Coefficients determined by partial derivatives and then moment terms. Now that's a formal power series at this point. If the Hamiltonian is polynomial in Q and P, only finitely many partial derivatives are non-zero, so we really have a finite sum and everything is well defined. If the Hamiltonian is not polynomial, usually these expansions give us asymptotic series, just like other semiclassical expansions. Here, if we use a truncation of moments, semiclassical means that moments decrease by a certain order of h bar if the full order of moments increases. So it's not just Gaussian or specific examples. It's a pretty large class of semiclassical states or moments. Now, to see how this works in a case where there is a potential, so no longer just the free particle, we have our previous PS squared, so kinetic energy, and C over 2ms squared. But then the Taylor expansion of the potential gives us another term at second order moments with second order of the potential and an s squared. That has applications in tunneling because we look around a potential which may have a local maximum somewhere, like a barrier. Then V double prime is negative around the local maximum. So the new term here decreases the classical potential. So if we make S large enough, it turns out there's a way to bypass the classical barrier while maintaining energy conservation. So the usual tunneling description, it can be described by completely classical motion. Here's an example. That's a cubic potential. So if you just look at the green line, that's what the potential would be classically, 0s here. But then the surface, it's not so easy to see on the surface, but if you look at the contour lines here, there is still a dip around the classical minimum. But there's a path opening up here around the classical barrier if we have sufficiently large S in energies. But the energy does not have to be larger than the classical energy required for transmission. So in this way, also a more geometrical or classical description of tunneling. Quantitatively, that's now a quartic potential, not the same example. Tunneling here is expressed in terms of tunneling time. So along these bypassing trajectories, we can keep track of time and determine how long it takes for our object to get through to the other side of the barrier for a given energy. And different lines here. So green line, of course, classically, we don't have tunneling. So at 1 here, we would reach the barrier in this example, tunneling times diverge. A second order, the red line, so this would be like the previous equations. We have a larger region in which we can bypass the barrier, but there's still a region in which the tunneling time goes to infinity. So second order does not give us a complete description of tunneling. So we need an extension to third order at least, which is the blue curve here. And that's, in this case at least, pretty close to the exact solution based on wave functions. So we need an extension of these second order S and PS variables to higher orders. Now, it turns out in general, these moments are actually pretty complicated. They have a few nice properties. They're always real by definition. They can be assumed to obey the semiclassical hierarchy to have a general definition of semiclassical states. They are Poisson orthogonal to the basic expectation values Q and P. So in this sense, they are kinematically at least independent of expectation values. But then the more complicated properties, they're uncertainty relations. And at higher orders, usually different independent ones, not just a single one. So we really have a phase space with boundaries, multiple components. So it can be hard to describe that without a detailed geometrical analysis. And then the brackets themselves between two moments are quite complicated. So they're certainly not canonical, as we've seen in the second order example. And at higher orders, they're not even linear. There's some quadratic terms as well, and a complicated summation. So it's a pretty complicated Poisson bracket. And fortunately, at least for some orders, we were able to find examples of these Casimir-Darboux versions. So these are the more recent results. Now, the bracket is pretty complicated. The Casimir-Darboux theorem is not constructive. It's an existence theorem. So it doesn't really directly tell you how you can get these S and PS parameters. But there are at least some method that turn that into a procedure of solving multiple differential equations. And we've solved them in some cases. So one example is here. So for a single particle, we extended this mapping to fourth order in moments. So that's given here. So that's a 12-dimensional phase space. So we have 5 canonical pairs, S's and P's, and 2 Casimir variables, C1 and C2 at this point, 2 constants. I write only 4 equations for moments because all the other moments can be derived from them using suitable Poisson brackets. And so what we can see here is we still have the kinetic terms, or momentum squared in the momentum fluctuation, but then it's no longer just a single 1 over S squared. There's some kind of repulsive potential between different S variables. And then higher orders are higher order polynomials in the S variables. So that's something, the third order version is something we used here for the blue curve. Now, the other extension, of course, that's necessary is to multiple degrees of freedom. And also here, the number of degrees of freedom, number of moments initially multiplies. So what we've done here is a second case for, second order, but 2 classical degrees of freedom, x1 and x2. And for second order, it's still a linear system. It's actually related to the symplectic Lie groups, Lie algebras. But also there, for general cases, it's not known at this point how to find the mappings. But for these 2 degrees of freedom, we have one written here. So delta x1, delta x2 initially still very simple, just the S variables. The covariance between the 2 positions, now that's already geometrical. It's another parameter beta, which is one of the canonical variables in the sense of Casimir-Darboux. It's described here by an angle. So the it's like the angle between the 2 directions in momentum space, in moment space. Now the momentum of p beta. It appears in delta x1 p2, which I didn't write here. It's not a very complicated expression, but it also appears in the individual momentum fluctuations, which unfortunately at this point are more complicated than for single particles. So they still look like p squared plus u over s squared, but u is no longer constant. It's not a Casimir variable anymore. It depends on the two momenta, well, p beta and then a p alpha, which we haven't seen yet, but it's the fourth canonical degree of freedom. And it appears in these u functions, u1 and then a u2 for the second momentum fluctuation. And pretty complicated dependence on beta, and then again this alpha, which is another canonical variable. So that's a complete canonical description, but we're still working on the physical or geometrical interpretation of all these terms. In a simple case, if we can assume that this p alpha and this C2, the second Casimir, are much smaller than p beta and the square root of C1, which we understand a little bit better. P beta is related to that angle for correlations, and C1 is like the previous C parameter for a single degree of freedom. If these two terms, or any term in which these two variables disappear, can be ignored, then delta p squared is, it simplifies, and it again has the form of a centrifugal potential now in 3 dimensions. So there's a 1 over s squared and 1 over s squared sine squared beta, which can be interpreted as a 3-dimensional centrifugal term where one of the spherical angles is just beta, the correlation angle, and the second angle, like before, would be spurious. So that's just introduced to get a Cartesian description. P beta is then the momentum of this theta angle, or in this direction. And p phi is again related to a constant Casimir. So this would also be bounded in some way by uncertainty relations. So just like in the free particle, also in this case, we can model quantum uncertainty, the bounds that implies, through a centrifugal barrier in now 3 dimensions for the fluctuation space. So again, a geometrical description. Now we still don't really know what this alpha, p alpha, and C2 mean, so they don't appear in this centrifugal description. But we at least have an indication or a conjecture. In the paper that the last ones I cited, we did a calculation to compare with standard effective potentials, which are usually determined by some minimization procedure. So we can use the Taylor expanded potential with these canonical variables inserted and minimize the fluctuation dependence, keeping the classical expectation values unrestricted. So this can be seen to give equivalent results to other standard methods, path integral methods, for instance. But it does not determine alpha or p alpha or C2 in this procedure. But it's an expansion around the ground state. We minimize the potential. And the ground state should be determined by a unique wave function. So there should be a unique state corresponding to the minimization of the potential. We don't get a unique result for our moments because they are undetermined parameters. Now the moments may be for a pure or a mixed state. So one possibility is that these parameters that we don't know well yet or understand well yet might be impurity parameters. So they might describe deviations from the pure states. And then in combination with additional higher order uncertainty relations, there would be boundaries which push them in a certain direction as we approach the ground state to make sure it is really a pure state. So this would explain why these parameters are not determined by minimization. They would be determined by being pushed into a corner as we approach the ground state by boundaries from uncertainty relations. So we're currently testing this conjecture in different ways for specific states to see how these simple parameters might be related to other measures of impurity. And if that can be made more precise, it would be an interesting description, again, classical or geometrical picture for impurity.
Martin, you, oh, okay.
Yeah, I'm concluding right now. So yeah, so I just gave a few examples here of these geometrical insights that we can get from our canonical description of effective theories or quantum theories. And we've seen how that unifies and also extends previous approaches, which have already been useful in different fields, and there might be more applications in the future. One advantage is that, at least so far, the orders we've been able to consider, it's pretty efficient once we have a Casimir-Darboux description and also intuitive. Of course, the tricky part is deriving these Casimir-Darboux variables, but it's good that they are independent of the dynamics. So once we have it to a certain order for a certain number of degrees of freedom, they can be used for all kinds of potentials. So once that time has been spent on working that out, it's will be useful in all kinds of cases. Of course, it has to be extended to higher orders, more than 1 or 2 degrees of freedom, classical degrees of freedom, and that's still in progress. But it already allows us to characterize states and distinguish between classical and quantum states, and maybe at some point couple them in a different hybrid version. I also want to mention, just to conclude, since the Jacobi identity has been discussed previously in talks today, we've applied similar methods to non-associative quantum mechanics in which the Jacobi identity is violated by this non-associative nature. So there might also be a way to extend them to other non-Jacobi systems like Koopman cases, but we haven't looked at this yet. It's just as a suggestion. So thank you for your attention and the invitation again, and we'd be happy to discuss more.
Great, thanks very much, Martin. Are there questions? Yes, go ahead.
Yeah, just a comment. Maybe I didn't understand correctly, but in one of your first slides, you hinted that the Koopman hybrids do not preserve the uncertainty principle on the quantum variables. Or was that true? Is that what you mean here?
Well, a different version. So what I meant here is the uncertainty principle in quantum mechanics is derived from positivity of states.
Right.
And positivity might be violated. So there might still be an uncertainty relation of some form, but it could give rise to a smaller parameter instead of u.
So what happens is that no matter what the joint density is doing, the density matrix of the quantum subsystem is still positive definite, always by construction. And therefore, as far as the quantum degrees of freedom are concerned, their uncertainty relation is preserved by construction.
Yeah.
Okay.
Yeah, right. And if it's quantum, it is. But
Right.
if you apply this to a classical system.
But for classical systems, there is no uncertainty, right?
Right. Yeah, that's right. I mean, I'm not making a new statement here. I'm just reformulating it in terms of this U parameter.
Okay, sorry,
Which then appears in the free particle example. So that would be actually be C here in this case. So it would have a different lower bound for the impact parameter.
Okay, I just misunderstood. Okay, thank you, sorry.
Dennis, do you have a question?
Yeah, I have a question, Martin, about the very good talk. You use a tunneling time to benchmark with exact simulations, and tunneling times are, first of all, there's no single tunneling time definition. It's very poorly defined terminology. I was wondering, why do you choose to use this metric? For example, why not to simply the probability of tunneling means what's the probability of being in the classically forbidden region of the phase space, which is of course well defined and it's not subject to any interpretation. That's my first question. Second question, could you just once again remind this physical meaning of S variable? Why would you have a centrifugal force suddenly? Like, why would it act as a centrifugal force in these settings?
Yeah, let me first address the first question. So the tunneling probability is actually more complicated in this formalism. And we still don't understand it well. We're still working on how to get a good estimate in this case. Because we would usually deal with this just like a classical system. So you start with fixed initial values somewhere in this in the trap region, and then evolve. So for a tunneling probability, we would have to do something like evolving multiple trajectories and then somehow determining how we would say some of them have tunnels, some of them haven't. And yeah, we're still working on that, but it requires more statistics. It's easier in this approach to use tunneling time, even define it without using all the controversial other definitions, but really just looking at a trajectory here in this plot. And so from the initial values, you can determine the energy, you can determine the 2x values where you would enter and exit the barrier. And then along the trajectory that you get, you can just determine how much time it takes. So that's what we did here with the colored curves. And what's exact here is based on a wave function, not on previous definitions of tunneling time, but also just evolving an initial Gaussian in this case, and then checking when its expectation value reaches the end of the barrier. So that's what we used as a definition, and we have agreement. There are other definitions of tunneling time, but this one is related to expectation value. So that's the most natural comparison here, because the color curves are also based on evolutions of expectation values. But does that answer the first question?
Yes, yes, thanks.
The S variable.
Sorry, Martin, we're beyond time, so maybe I'll just, and Irene has a question, so maybe Irene ask the last question, and maybe in the break.
Okay, thank you very much. So you have this these hierarchies of coupled moment quantities. Do you actually use a variational principle like to effectively truncate these hierarchies, or do you have other truncation procedures?
Well, what we do right now is pretty much brute force. So we would just by hand remove anything that's beyond a certain order in H bar. It's related to time-dependent variational principles. At least what we've used so far is, at least in the Gaussian approximation, there is a clear relationship.
Yeah.
And yeah, that's one way we are exploring right now to see if that could give rise to better truncations or more adapted truncations to specific cases.
Okay, thank you.